Good afternoon. My name is Alan Buehrig with the Idaho Transportation Department. Myself and Mike Johnson this afternoon are going to share with you a presentation about load rating railroad car structures using BrR. So in Idaho, for the Transportation Department, we manage 28 railroad flat car structures across the state. All of those are owned, or they're all part of our local system, and the inventory dates back to about 1930 to present. Although I think in more recent times, we're seeing a lot of other cost-effective bridge alternatives competing with the used railroad car market. Prior to 2016, we chose to rate these structures using engineering judgment, and that was mostly based on the MBI condition rating of the structure rather than an actual computational analysis. And I think that was in large part due to the remoteness of these structures, as well as just the complexity. After 2016, we started getting a lot of pushback from Federal Highway to complete analysis on these structures because they could be drawn up, they could be quantified and rated. Our initial attempts to do so, just straight input into BrR, often led with or yielded overly conservative results. So 2019, we went out to a contract with Wisjini Elstner, or WJE, to load rate 13 of these structures. For today's discussion, we're going to focus on 5 of those. Kind of start off a little bit more broad, and then towards the end of the presentation and passing off to Mike, we'll get into some of the nitty-gritty BrR input and ways that we were able to make that successful. The first one, starting off with, is located in the near the Montana-Wyoming border, owned by a county agency there. The real takeaways I want to talk about with this structure are the traffic use, the relevancy of load rating markings, age of the structure, and some of the properties that we assume for steel strength and other things. And then, although we don't rate for them, the condition of the abutments. Here's a approach picture of that structure, and then a right side photo. You can see it was formerly owned by Union Pacific. And this structure had a posting on it prior to our analysis. We were unsure of where that had originally come from. The final posting with LFR analysis found the deck controlled the rating, and we were able to get that up quite a bit higher near legal loads. So the first thing I was going to talk about is traffic use. This is just beyond that last photo that was just taken. You can see on the photo on the left that this road really has low use. It was a dirt road and really and truly in the middle of nowhere. The reported ADT was about 5 cars a day, and that might even be generous. So I think one thing for us as we began approaching this exercise is to not lose sight of the use of these structures and the actual fatigue cycles and such. Next, talking a little bit about the markings on the side of these bridges. We got a little bit of pushback with some of our local agencies as far as the need and the amount of effort that we were expending to rate these structures. Why is that necessary? There's a capacity stamped on the side of the bridge. We did look at that a little bit during the course of our ratings. Of course, the loading scenario is completely different. And really, we found there's just too many different variables to make any use of those numbers. This is a photo of the underside of that structure. This structure was reported to have been constructed in 2007. but had more than likely been used at least one other location. And so that was one thing we kept in mind is the material properties. This structure was obviously it was a cast structure, which was kind of was cool to take a look at, but it was probably circa 1930 is when it was first originally built. So that played directly into steel properties that we assumed. This picture on the left shows a lot of these structures had many extra dead load components left over from their former life, as that picture shows. And then the photo on the right, we found that in many cases, the abutments that these structures were placed on were not engineered, and in some cases had adverse effects on the support conditions and span lengths that we were assuming for these structures. Next bridge I'm going to get into is located in the center of the state, owned by the local highway district in a pretty short span. This first photo on the left shows the bridge in kind of the dead of winter here in Idaho, and the elevation photo on the right. This structure, this schematic here was drawn up by WJE for the purposes of load rating the structure. This was 2 railroad cars side by side. There was a main member down the center with exterior channels, and then floor beam and diaphragm kind of supports. Those exterior members, those channels were really pretty light members, and then the main member was an I shape. We ultimately posted this structure near legal loads. So looking at the underside of this structure, kind of leave you scratching your head a little bit as far as how this bridge actually works, how load gets transferred. This arrow I'm pointing at an exterior channel, and asking the question: is this really, this is spanning from abutment to the abutment, but is it really a girder element? And then additionally, these members that are cantilevered off the side of the main member that extend over to the channels, are they floor beams, or are they more diaphragms? So our consultant WJE actually completed a finite element analysis on this structure, looking at both dead load conditions and live load conditions, because the load path between dead and live load was different. Here in this slide, I've used line weights just to kind of conceptually show relative stiffness and really the need for the finite element analysis. Show those exterior girder members alongside that main member. They were really pretty flexible in relationship to everything else. So for the dead load analysis, those channels were found they could hardly support dead load demands if they were treated as a girder element. And so really the way that this bridge worked is that those exterior channels acted more as a multi-span or multi-supported beam, and the load was being transferred back through those cantilevered members back to the main girder. Which then, in order to make that happen, we had to look carefully at this connection as far as the stiffness of that support, and how that would be modeled to be able to transfer that load from those exterior channels back to that main member. So WJE did some research and looked into some similar connections and some work that had been done in research, and ultimately was able to come up with a K value for rotational stiffness that was assigned to that connection to transfer that load back, and that's what was put into their finite element analysis, which was used. They used CSI Bridge. So then the live load path was actually totally different. There's an 8-inch concrete deck over the top, which was stiffer than those floor beam elements. So really under live load conditions, they acted more effectively as diaphragms. Here's a screenshot of the finite element analysis, kind of an isometric view, showing that deck was modeled using shell elements. And we don't normally rate the deck we don't normally rate the deck in Idaho if it's a concrete deck, but in this case we wanted to check ourselves on. We wanted to check to see that load could actually be transferred back to those main members through the deck. So there were some assumptions that were made by WJE, and then ran an analysis to verify that the deck really could take load back from the exterior girders to the main member. And ultimately, from the finite element analysis, effective distribution factors were calculated based on the different trucks and for the different girder elements. This calculation here was for the SU7 truck, looking at one of the exterior channels, and really showed there the effective distribution. In this case, the effective distribution factor was 0.07. So really, those exterior channels were quite flexible and not efficient in carrying load.
I'm sorry, I'm going to interrupt. Can you see the screen?
Yes, I can see it now.
Okay. Sorry.
The final structure I'm going to talk about is located in the northern part of the state, one of our larger spans at 70 feet. And this one was in actually poor condition. So our load rating takeaways from this one, looking at, there was some fatigue cracking from its previous life, looking at span lengths, modifications that are often done to these railroad car structures, the load path again, similar to the last one, and then looking at transformed sections and how do we successfully input some of these unique sections into BrR. Here's a picture of the approach, and then the right side. This was this had newly been installed as of 2019 and didn't have a current rating on it. Here's a picture of the underside. You can see there's a large main member, cantilevered members extending off from that main member, exterior channels, and then a stringer system above. So in this case, that main member was a built-up member. It was comprised of a couple channels and then a flange plate, top and bottom. So this structure, upon its first inspection, found that there was fatigue cracking back at the pin locations where the floor beam extended across the main member. Here's a zoom up photo of that coping in the web of that main member that allowed that transverse floor beam to pass through at the former axle location of the railroad car structure. And there was at that coping, there was a little bit of a fatigue crack extending out of that jagged cope. WJE, in addition to completing a site visit and drawing this bridge up, was actually able to successfully mitigate those cracks for us and just alleviate that concern and bring up our MBI rating. And that crack existed at 4 locations. So even though it was a new structure to the county and had just been put in place, it definitely had problems from its previous life. Another concept we want to quickly go over is span. So all of our structures that we found here in Idaho, they're all spanning from tip to tip of the flat car bridge, as opposed to the pin location from which they were originally designed and used. And in some cases, that distance from the tip end of the railroad car to that pin was as much as 8 feet. And so for these short span structures, it definitely played into a role as far as these, even though they had been designed and they were never designed for the conditions in which we were often using them. Also, many of these structures, I think, as inherently being a low-cost bridge alternative, they had many modifications. A lot of those modifications, even though we do inspections, don't really fit very well into MBI reporting data. And we found it was important for us to complete a site visit and for our consultant rating these to look at all the different issues. And it was often some of these modifications that controlled the rating. Here's a close-up of that picture that was on the right on the last slide. This is of the small floor beam members, and there's a large hole that had been put in there. And that hole and this location actually is what governed the rating and shear. And in this case, we actually provided the county with information as far as if they were to repair that hole, they would be able to bump the rating up a little bit. Additionally, load path. I think load path was a concern on all these structures and really required kind of taking a step back sometimes. And even though they're simple small span structures, often that was kind of a little bit of a complicated load path sometimes. This one had large floor beams alternating with small floor beams. Those large floor beams were cantilevered off the main girder, really quite a stiff element. And those smaller floor beams really kind of acted as a simply supported between the main girder and the exterior channel. Here's kind of a sketch. We made numerous notes and stuff on the previous sketches from what had been drawn up on these railroad car structures. But you can see the large floor beam members alternating with the small floor beam members, and of course, to add in complexity on many of these structures, we had a changing cross section on the main member. So as many of you are aware, a built-up section like this on the main member, what's shown here on the left, it does not fit nicely into BrR. So we had to split that up into equivalent I-shaped sections, which those were put into BrR, and WJE completed some additional external checks to really look into lateral torsional buckling, look into could this section actually go into plastic, could we use the plastic moment, and would the results on using this workaround, could we use these idealized I-shaped sections? We used these transform sections also on a number of our stringers. Often we had funky shapes of Z-shaped members or built up channel beams, and those were often idealized with just I-shaped members with similar properties. So from here, I'm going to pass off to Mike Johnson, who already has control, and get into some more of the nitty-gritty stuff.
And I apologize for that technical slide issue. If you still are seeing something awkward, let me know and I can change it. But I'm going to start off with the bridge up in North Idaho. It has a 50-foot span in satisfactory conditioning. Again, the posting was based on historical analysis, which we're not really sure where that came from, but what we ended up being able to do with these further analysis is increase the load posting on this bridge. There's just a quick view of the typical section and the roadway section coming up and the bridge. And here's a typical section through it. It's a 16-foot out-to-out with about a 15.5 curb to curb. It's three main supporting components longitudinally, where you have a main box beam in the middle, then you have some channels exterior. They're miscellaneous channels, 18-inch deep, and then it has some 4-inch deep stringers being supported by the floor beams. And it's similar to what Alan just talked about in the last bridge, where it has these deep tapered floor beams and intermittent with some smaller channels. Now you can see that these main floor beams that are tapered, they're spaced at 5 to 6 feet apart, not real accurate. I mean, they're spaced kind of sporadically. And we also have these smaller channels that are spaced closer together in between the tapered channels. And they're relatively small size. They're 6-inch or 7-inch deep channels. The main tapered floor beams span from the main beam all the way out to the edge of the deck. Whereas the smaller channels, similar to the last bridge, span between the exterior channel beam and the main box beam. Here's a little underside view so you get a little better view of it. You have your tapered floor beams with your channels and your stringers running on top of them. And these channels are supported, these small floor beams are supported by the exterior girders and the main box beam. Well, we had to define the properties for the atypical shapes, similar to what Alan was talking about. So these are highlighted are the ones that we actually had to put in using some idealized shapes. For this box beam, again, we had to calculate what the section properties were. And in this case, we're going to input it into two different models. One where the beam was idealized by a single, that box beam is idealized by a single I-shaped beam. And then we have a revised model that it uses two I-shaped beams to represent that box. We had to start off by checking and make sure that if this box beam is a compact section or not, checking using the equations in AASHTO to see if the flange or your web local buckling is an issue. In this case, they weren't, and it was a compact section. And then the next step is we wanted to check and see if lateral torsional buckling was. We started off by using the equation that's shown in the middle of this screen, and we got it out of Salmon, Johnson, and Melhouse. It's also in the LRFD AASHTO code commentary, where you have your MCRAC is represented by this equation, or sorry, not MCRAC, M critical represented by this equation. When we calculated, we got an M critical buckling of 27,000 kip feet. And as you can tell, comparing it to the plastic moment and the yielding moment, it's significantly greater. So we were pretty sure that lateral torsional buckling wasn't going to be an issue, or at least the controlling. So we went back and in the America codes, AASHTO, and in this case we used the AISC because it better handled this built-up box type structure or members. We calculated to see if where we were, if it was going to be plastic, elastic, or somewhere in inelastic buckling. And we found that it's slightly, you see the unbraced length of 43 feet is slightly greater than the plastic limit. So we had to go in and use the equation for the inelastic buckling. And we found the capacity of 1989 kip feet. Well, that was using a conservative assumption of 1.0 for your CB value. And CB, just bring you back to the basics. CB is kind of dependent on how the beam is braced and loaded. And here's some typical cases shown on the screen. And where we're at is down here in the bottom left-hand corner, where we have bracings that were kind of sporadic and in there, and the loading is definitely moving. And so what is our CB value? We knew it was going to be somewhere greater than 1 and probably between 1 and 1.13, but we didn't really know how to do it. And I showed the equation on how to calculate it. It is 1.75 plus 1.0 times this quantity of this ratio of moments, M1 over M2, and then plus 0.3 times the ratio of those moments squared, where the M1 is the smaller of the moments on either end of the unbraced length, and M2 is the larger. Well, we didn't want to calculate what it was for all the different locations and loadings and all that, but we felt that if we can figure out, we know we're somewhere above 1, and so when we compared our actual capacities to what the M plastic was, they were basically 1.0, and we felt very comfortable for both of these bridges that we can use the full plastic moment capacity. We also want to note that if you don't have that, you will have to go back and change your section or hard code capacities that you use in BrR to actually give you the correct value. So don't just put something in and assume it's going to be correct. So we came in here and like I said, we're going to use the full plastic moment capacity. In order to get the full plastic moment capacity for the I section, we've fully laterally supported the top flange. And like I said, if you want to adjust it, you could either change the section properties in BrR to match that capacity, or just hard code it in. We did the same thing for the other sections, like this exterior girder, and then we also verified the capacity that we anticipated. So we used the same bridge, and we looked at it 2 different ways. One, like I said, we used a single member for the middle main box beam, and then we also input the exterior channels as girders, and we had floor beams spanning between the 2 and stringers on that. Then we revised the model, had the model revised by WJE, which actually took a look at the box beam as 2 separate members with floor beams, and all the other stringers / channels were being acting as stringers, acting through the floor beams onto the main box beam. I mean, here's a quick look at the input of it. We have the floor beams that we put in. The 2 different stringers represented these 2 smaller 4-inch stringers, and then the 3 different girders. The girder 1 and 3 are the channels, and then girder 2 is that main box beam. And then we have comparison. Here's how we put it in. We have the floor beams. We put in the stringers, which now the stringers, we have several different, or another different definition, and we just have the 2 girders represents just the main box beam. When we put in the floor beams, we put them in both on both models, spanning between all the floor beams. So we have all the floor beams in, even the smaller channels. And like I said, you have to come in here and decide how it's going to be, the live load is going to be distributed. And in this, on the right hand or left hand side, we have the original model that, again, that main box beam is represented by one single floor beam. And so we based our live load distribution factors based on stiffness compared to those exterior beams, trying to take in consideration that you can get a little bit of torsional effects on the exterior beams. So we were close. We were assuming that most of the load was going to go to the exterior beam. It's almost 2 wheel loads. Where on the other one, remember, we're putting all the load onto the main box beam, but we're representing it as 2 different members. And so it's a 1 wheel load per girder that is applied to this main girder. And like I said before, we're going to laterally support this to make sure that we get the full plastic moment capacity. And when we compare them, the 2 different members, we get very similar results for our capacities. We had slight change in dimensions on this because we went out there and measured it during the between the 2 models. But you look at it, we're getting very good results. So we ran it, got our ratings for all the members. You can see these are the 4 different members that we looked at when we were building the model. We have the exterior girders with a rating factor, and then the main box beams on top right. Then you have the stringers, and then the floor beam. And the floor beam, the one that we're looking at, is the smaller channels. And I will talk a little bit more about this a little later. But you can see the relative rating factors. But you have to remember, we're estimating what the distribution factors are, so keep that in mind. Now, on the exterior, or the revised model, you see the main girder had a rating factor of 1.0, which is similar to the last model, but you'd expect it to be a little lower because we did assume that it was taking all the load instead of only partial. You also have similar rating factors for the stringers, a little different because we changed, again, the measurements changed with the section we used, section property we used. And then we have a rating factor for the main floor beams that we were able to obtain through our model. We weren't able to get the ratings for the smaller floor beams, those small channels, because they were assumed to act the same way as the main stiff floor beams. So we had to go back and calculate the capacities of those using hand calculations. And you can see you're getting rating factors for shear above 1, and for moment it's just below 1.0 for HS20 truck. But each model has its limitations, and each model you have to be careful when you're using it. For the original model, we had to make an assumption on what the live load distributions for each girder were. And without any further guidance, we kind of took the relative stiffness for each and then modified it a little bit because you're going to have some loading effects if you move the vehicle all the way over. Also, that exterior channel was modeled so it spans from abutment to abutment. So that's not realistic because we understand that these big, we call them pork chop floor beams, are actually supporting it. So it should be supporting not spanning between these deep floor beams. And you need to check in everything that your results actually match what you thought you were modeling. Here's the small floor beams, and I told you I was going to talk about that, the rating of that small floor beam, and we had a rating factor of 0.57 or 0.56. Well, if you look at the screen and you look at the capacities that we calculated, we were able to match the capacities, but we were not able to match the loads. And if you start wondering, okay, is one wrong, is one right? No, it was just different. The way we modeled it in BrR, how we had to model in BrR, really wasn't how we wanted it to be modeled in real life. And so we went in there and had to modify our rating based off of this updated calculations. Now, in the revised model, it has limitations because we're assuming that these exterior girders are supported by all the floor beams in the model. In reality, it's just being supported by the main floor beams, and it's supporting those smaller channel floor beams. So the exterior girder may be underestimated in how much load it is carrying. Also, you need to check the channel floor beams because those, we're assuming that they're acting as cantilever and supporting those exterior beams. Well, like I said, we had to do that exterior calculation in order to get a rating factor for those. We're also underestimating the main floor beam loads because of how it was modeled, so you have to go back and adjust for that. And this model didn't address the timber deck. So additional analysis may be required. For the deck, you could come in here and put another model in to analyze just the timber deck. That's pretty easy to do. And also, for the exterior girders and the main floor beams, you can put in a separate model that takes out those channel floor beams, and it'll give you the results for those that more accurately evaluate that. It's just a lot of work. So you might have to have 3 different structures, superstructures in this model. Another option is to do external calculations and to supplement your BrR model with it. Well, I'm going to quickly go over in the next couple minutes what we did on another bridge, just about the same bridge except for, I mean, actually it's only a third of a mile down the road. And it's very similar except for the main girder, instead of being a box beam, it had separate webs and flanges, bottom flanges with a shared top flange. And also the exterior girder was a built up section instead of a channel. So we didn't trust that this exterior beam was going to, or this main girder was going to take all the load because of it just wasn't torsionally stiff. It had some tie plates at the main floor beams, but they are all cracked, as you can see in this picture, and they did not transfer load. Just to note that the cracks did not propagate into the base metal. They also, on these exterior channels, or girders, they notched out some areas that we had to account for. So we did a finite element model to do it, and here's a quick look at it. Everything in red is plate elements, and then we have blue that are modeled as beam elements. Every component was modeled in this CSI bridge file. We took that and we were able to get what we did section cuts at each girder, and we were able to get what the moments that were being transferred into those girders. Like the main girders, we got the dead load moments, and we turned them into equivalent distributed loads so we can input those into our BrR model. We did the same thing for our exterior girder. Now, live load moment distribution factors, we calculated by taking the moments that we received from the CSI model and compared it to just a simple span calculation for a HS20 live load on just a simple span. And you take the CSI model loads divided by your hand calculations for just one truck, and you come up with a distribution factor. Here's what they are on the highlight, the live load distribution factor based on a lane of HS20. We also did this for all the legal trucks that we were rating. And you can see these were for a lane, and we had to convert them into wheel loads to put in for LFR. Now you have to be careful if you're using lanes or wheels, depending on what method you're using to analyze it. And you can see what we did on this exterior girders, we took the one we calculated and we doubled it. Well, this is for HS20. The one on the bottom is for, I think, the controlling one, which was the type 3. Well, for the main girder, remember, we modeled it as a single girder, and we had to convert it into two separate girders. And so you take half the load that you got from CSI, and then you multiply 2 to turns it wheel to lanes. And then we use that to develop our distribution factors in BrR. And so you're asking, why are we using BrR if we have to do all this work? Well, in Idaho, we don't just use BrR to load rate or design. We manage our inventory. We rate the bridges. We do permanent analysis on these bridges. We also can use it to reanalyze in the future for changes like additional load or deterioration. And the final thing we feel it's important is we can analyze something like this for situations like this where the cutout, where we use the live load or the deterioration in BrR to calculate what this rating factor is. And with that, I thank you very much for your time.